Hello everyone, it's Mrs. Hanson once again, picking up with our lessons in our Chapter 1 of Organic Chemistry, Section 5, called Polar Covalent Bonds. We understand bonds, a shared pair of electrons, can be one of several categories. It can be a non-polar covalent bond, where the electronegativity difference is less than 0.5. When you see me write EN, just know that that stands for electronegativity. And again, review from probably your first semester Gen Chem. Those examples, if I look at carbon's electronegativity value of 2.5 and I subtract the exact same number, we're going to have an electronegativity difference of 0. Any element bonded to itself would be a non-polar covalent bond. And even carbon, which is 2.5, with a hydrogen, which is assigned a 2.1, gives us an electronegativity difference of 0.4, which is a very negligible difference. They are considered to be non-polar covalent bonds. If we have an unequal unequal electron distribution, we have a polar covalent bond. And the electronegativity difference would be between 0.5 and 1.7. Carbon, with its 2.5 electronegativity value, compared to oxygen, which is 3.5, gives an electronegativity value of 1.0, which lies in the polar covalent region. Notice that we use special designations to indicate the induction of charge. Carbon to oxygen, we use this tail at the end of an arrow, and we point to the more electronegative element. Carbon is less electronegative, resulting in a little positive charge, and oxygen, which is more electronegative, more electron-rich, gives it a partial negative charge. So here we can see electron deficient gets that tail portion of the arrow or the positive symbol, and electron rich gets that negative region. And we can represent polar covalent bonds with those types of symbols. And if the electronegativity difference is so large, greater than 1.7, it's not covalent, it's not sharing at all, but it's more of an electron transfer, and that indicates that we have ions. Notice that the 0.9 assigned from sodium, when compared to oxygen, which is 3.5, Na plus and OH minus will be a sodium ion and a hydroxide ion, giving an ionic bond. So based on electronegativities, we're able to figure out what type of electron sharing is occurring. Sometimes we have an electronegativity difference that is right on the edge of these arbitrary signs of being polar covalent or ionic. And as an example, we see a carbon to lithium bond. When I take a carbon, which if you remember is assigned 2.5, and lithium, who is assigned a 1.0, and just to verify, lithium is 1.0, we can see that that electronegativity difference is 1.5, which is very close to the 1.7 that is arbitrarily selected as being ionic. And so what is correct? Do we show it as a shared pair of electrons, as a covalent bond, or do we show it as ionic, with the carbon, which is the more electronegative, having a negative charge? Remember, that's its formal charge. And lithium with its +1. And the answer is yes, they're both acceptable to write either way, polar covalent or ionic. And just keep in mind that this Linus Pauling electronegativity values is just one of many methods for calculating these differences. So if it's close, you're not going to be marked incorrect because both are acceptable. If you write one or the other, both are correct. More of this skill in this level is to identify polar covalent bonds and results from inductive effects placing those partial charges. And so the partial charges, just to remind you, could be the arrow, which the positive tail is going to represent the more positive region, and then the more electronegative element is being pointed at. Or you can use these little Greek symbols for partial positive or partial negative. Both of those symbols are used to show polarity inside of a bond. So let's find all the polar covalent bonds in this structure called methanol. And remember, we had just said a carbon to carbon and a carbon to hydrogen, you should just flat out memorize. These are non-polar. So right off the bat, I can eliminate those 3 bonds as not being polar. Here I have a bond between carbon to oxygen, and that clearly has an electronegativity difference that falls in the polar range. And who is the more electronegative element? Ask yourself, who's closer to fluorine? And that would be oxygen. And so the bond polarity is pulling the electron density towards the oxygen, leaving the carbon electron deficient with a partial positive charge, and the oxygen as electron rich, giving it a partial negative charge. And there's also a polar bond between the hydrogen and the oxygen. The oxygen, again, more electronegative, is pulling the electron density towards itself, leaving the partial positive charge on the hydrogen as well. So that induction, the withdrawal of electrons towards the more electronegative element, is shown either with these partial positive or partial negative signs or with the polarity bond arrow. Shall we try another? Oh, that's our answer from before. We had said methanol could be used with an arrow or with a partial positive, partial negative. And so we had just drawn those. But let's try some more from homework. So I just selected a few from your skill builders, and right off the bat, just notice that the carbon to hydrogen are non-polar. So take those right off the plate. We're not going to have to indicate any type of polarity there. But I do see a carbon to oxygen bond in both of these directions, noticing that the carbon is electron deficient. The oxygen would be electron rich, so I can see the partial negative on oxygen and each of these partial positives on the carbons. This is a mirror image. We have a carbon to oxygen bond here, making this bond electron deficient at the carbon and electron rich at the oxygen. And now we have all of those symbols placed in there to represent the partial positives and partial negatives in those polar bonds. So I see 4 polar bonds, all of them being the same, carbon to oxygen. Letter B, CH are non-polar, so they're uninteresting to us. The carbon to fluorine is a very polar bond, making the fluorine, who is the most electronegative element, very electron rich, and the partial positive left on carbon. Same idea here. Carbon having its electron density being pulled away from it towards the chlorine, making the chlorine electron rich and the carbon electron deficient. And in letter C, I also recognize that there are 2 polar covalent bonds. The first between magnesium and bromine. Bromine, of course, is more electronegative than magnesium, making bromine very electron rich and magnesium very electron deficient, positively charged. Carbon is more electronegative than the magnesium as well, making carbon here electron rich in comparison to magnesium. We have identified 2 polar covalent bonds in structure C. We've identified 2 polar covalent bonds in structure B, and all 4 polar covalent bonds in structure A. Our next section reviews atomic orbitals, those s, p, d, and f-shaped orbitals from quantum mechanics. This is the section where you learned how to write electron configurations, 1s2, 2s2, and so forth. And so just a little quick review of quantum mechanics back in the 1920s was the established theory that explains the wave properties of electrons. The solution to these wave equations gave us wave functions, and these functions, which were psi squared, gives us these images of atomic orbitals. We know that an S-shaped orbital is a sphere, and a P-shaped orbital looks like an hourglass. If the hourglass, these P-shaped orbitals, are aligning itself on the y-axis of an x, y, z three-dimensional, we called it P sub y. If they're aligning itself on the x-axis, we called it P sub x. And P sub z is our third spatial orientation for P orbitals. Notice that these P sub x, P sub y, and P sub z are all of equal energy. And we need to remember that vocabulary word called degenerate. It means they're of equal energy. An S is of lower energy than a P, which is of higher energy, but those P orbitals are of equal energy to one another, so those P orbitals are called degenerate. When we're filling atomic orbitals with their electrons, there were three rules or three guiding principles that allowed us to place electrons. The first of those three is called the Aufbau Principle. Simply stated, the Aufbau Principle says the lowest energy orbital is always filled first. Keeping in mind that that means that the 1s orbital is always filled with at most 2 electrons. The 2s orbital fills next with at most 2 electrons. The 2p orbital fills px, py, pz for a total of 6 electrons, and so forth. The Pauli exclusion principle reminds us that each orbital can accommodate the maximum of 2 electrons, but they must have opposite spin. And that means as we were writing our orbital diagrams, we would place 1 electron first and then partner it with an opposite spin. We would place 1 electron first and then partner it with an opposite spin. Hund's rule. When dealing with degenerate orbitals, such as the 2p sub x sub y sub z, 1 electron is placed into each orbital first before you partner up. So I had just modeled that. If I'm filling the 2s orbital, it fills completely. Then I start placing in the p's, 1 in each first, and then assign partners with opposite spin. Most students do very well in that section of Gen Chem. It'll come back to you with some quick practice. When we write electron configurations, let's review. So one of the tricks that I like to use is, I don't know if it's a trick, but it's just a visual to help me remember. I like to write the orbitals, and I'm just going to kind of create a column that says, in the first column I'm going to have all the S's, and I remember that S's fill with at most 2. And at the first energy level only has 1 sublevel, so I'm done with that. The second energy has 2 sublevels, so I'm going to just continue writing 2p, 3p, 4p in a column. And I know that at most the p orbitals hold 6 electrons. And in a third energy level, we have 3 sublevels, and the D's can hold up to 10. And the fourth energy level can have 4 sublevels, and at most 14. So that's kind of just a rough idea, and just kind of saying, I know that I'm going to fill 1s2. I hit the end of the row, so I come back to the top. 2s2, come to the end of the row, so I come back to the top. 3p, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and so forth. And so that little trick helps me remember the order of which we fill. And again, that should come back to you rather quickly. Now, on the periodic table, you find that carbon is atomic number 6, so we know to write for 6 electrons. The first of those 6 electrons are written in the 1s2, 2s2, that gives us 4 of the 6, and then we have 2p2 gives us a total of 6 electrons. So the orbital diagram, 1s2, 2s2, 2p2, where I have an empty orbital and 2 unpaired electrons. For oxygen, oxygen is number 8 on the periodic table, so we have 8 electrons to write for. 1s2, 2s2, 2p4 gives us a total of 8 electrons. You can see in the outermost energy level, there's 2 electrons in the s, 4 more in the p, giving us 1 that is partnered and 2 that are not in the p sublevel. And boron, which is element number 5, 1s2, 2s2, 2p1, giving us a total of 3 valence electrons, 2 of them in the s subshell, 1 more in the p, so a total of 3 valence electrons. What about if we see positive or negative charges? Remember that a negative charge means that it has an extra electron. If it has a positive charge, you have to subtract an electron because it lost that electron. So a negative charge, 1 extra electron. Well, up above here, carbon as an atom started as 1s2, 2s2, 2p2. But if we added an electron, instead of having 6, we now have 7 electrons, meaning that we'd have 2p3 as its total number of electrons. So carbon with an extra electron has an electron configuration with 1 more electron than its neutral atom. Same idea with carbon as a positive. It means it lost 1 electron. So if it had 6 and it lost 1, it means now that we're going to have 5 electrons. So lost 1 gives us 5. Gained 1 gives us 7 up above. Nitrogen on the periodic table is number 7. So 1s2, 2s2, 2p3 would give us the 7 electrons, but now that it's positive, it lost 1 electron, so we only write for 6 electrons. 1s2, 2s2, 2p6 is the nitrogen plus 1. By the way, that vocabulary word is called isoelectronic with carbon. In other words, a carbon atom and a nitrogen positive both have the same number of electrons, and that would be 6 electrons. And this is just a quick visual of what we've been practicing. Hydrogen with its first electron, 1s1. Helium with its 2 valence electrons, 1s2. Lithium has 3 valence electrons, the first 2 in the 1s sublevel, 1 more in the 2s sublevel. Beryllium, which is number 4, 1s2, 2s2. Boron, we wrote a moment ago, 2p1, and so forth. So writing those electron configurations is review from this section. In the next section, we talk about covalent bonding and the overlap of atomic orbitals. And this is known as the valence bond theory. When electrons are treated as waves, and remember we talked about one hydrogen atom kind of overlapping another hydrogen atom, and that's what they're kind of showing here. As they begin coming closer and closer together, the internuclear distance starts bringing them closer together. And those waves pass over each other with a constructive constructive interference, we have a bond overlap that forms for a covalent bond. If the bonds come together and they are in a destructive pattern where they cancel each other out, we get a node, and that's known as destructive interference. And so literally we just want to kind of envision the covalent bond is bringing, this would represent an S-shaped orbital overlapping with an S-shaped orbital, forming this covalent bond, and this could represent, for instance, one hydrogen to the next. An overlapping orbital, the valence bond theory. When those bonds overlap, and the major part of the density is located on the bond axes, this is what we called a sigma bond. All single bonds are sigma bonds. So for instance, if an S overlaps an S orbital, it's lying on the same axes, an S-S overlap is a sigma bond. I could have an S-shaped cloud overlap a P-shaped cloud head to head, and it would still have, now of course I should have drawn those actually overlapping, that would have been better. But it still has all of the electron density on the x-axis, so an SP overlap could also be a sigma bond. And if I kind of draw that a little nicer, here are some examples of sigma bonds as I tried to draw an SS. It's two spherical shapes overlapping in the same electron density as the x-axis. Here's an SP. Here would be a PP, an SP hybridization. Notice that even two P clouds could also overlap head to head along the same internet axis. So here we all have examples of sigma bonds, which means that the overlapping orbitals lie within the same x-axis. And when I say that, it's the same axis as the nuclei, right? That's where the nuclei resides, is in the center of the atom. So it's along the same electron density as where you find the nuclei of the atom. A pi bond, if you remember, occurs when orbitals overlap that are either above or below the axes of the nuclei. So if it's on the same axes, we called it a sigma. But if it's above the axes or below the axes, where the pi cloud forms from the p orbitals above and below, we call that a pi bond. Remember, the sigma bond are all single bonds, as well as the first in a multiple bond. And pi bonds occur as the second or third in a multiple bond. So for example, if we'd like to know how many sigma bonds and how many pi bonds there are in this molecule, let's begin counting as follows. All single bonds are sigma. I count 6 single bonds. And the first of all multiple bonds. So there I count 1, 2, for a total of 8 sigma bonds. Pi bonds are found by taking what's left, the second and third of multiple bonds. So I count 3 pi bonds in that particular structure. Of the 11 total bonds, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There were 11 bonds in that structure. 8 of those 11 are sigma, the other 3 are considered pi. All sigma bonds align on the same axes. All pi bonds overlap either above or below the axes. In this lesson, we talk about hybridized atomic orbitals, sp3 for example. When we talk about hybridized orbitals, what we're doing is promoting electrons from a ground state to an excited state. Let's kind of dive into this by considering methane, CH4. We had drawn methane a while ago, and it just had carbon as the central atom and 4 hydrogens attached to it. If I write the ground state configuration for carbon, just to remind ourselves, carbon is number 6 on the periodic table, so we need to write 6 electron configuration, 6 electrons in its configuration. 1s2, 2s2, 2p2 gives us 6 electrons. Knowing that these are the valence electrons, those that are interesting to the chemist, I have 2 electrons in the s of the second energy level and 2 more electrons in the p sublevel, leaving 1 completely empty. At this point, when we examine this, I only see 2 electrons available for bonding. A bond is a shared pair, so in order to share, I have to have an unpartnered electron. And right now, this configuration would make it seem that carbon only has 2 electrons available for bonding. And clearly we know that that's not the case because carbon forms 4 bonds. So how does it achieve this? When we write an excited state configuration, we're going to promote 1 electron from the 2s orbital into the empty orbital of the carbon's p sub z. So a moment ago, I had both electrons in the 2s, and I had 2 electrons in the 2p sub z. I'm going to take that in x. 2p sub x, 2b sub y, 2p sub z. But I'm going to take this electron and promote it to the empty orbital of the 2p sub z. It's like giving everyone elbow room. I have an empty bedroom and somebody's sharing in the 2s. I'm going to allow this to just be promoted to that empty space. And when I've done this, I'm actually hybridizing the orbitals to be degenerate. Remember what degenerate means? It means of equal energy. So instead of having a lower energy of S and higher energy of P, I now have 4 equal energies of an sp3 atomic orbital. An sp3 is a hybridized orbital that was obtained by promoting the s electron into the empty p sub z. Now I want to make this clear. A 2s energy level and a 2p energy level, the hybridized lies between them. I'm promoting the s, but it's not quite as high as a 2 sub p. I have 4 equal energy levels, and now I can clearly see why carbon has room to form 4 bonds. This then gets abbreviated as sp3. All sp3 hybridized energy levels promote the electron from the s orbital up into the p orbital to create 4 of equal energy. These are all tetrahedral in molecular geometry. We have a central atom carbon, 4 hydrogen attached back, and the molecular geometry here for an sp3 hybridized orbital is called tetrahedral. There are 4 electron domains. An electron domain is either a bond, just one word, bond, or lone pairs. So here I can see 1, 2, 3, 4. My exponents have to add to 4. So S1p3 gives us 4 electron domains. We call that an sp3 hybridized orbital, and bond angles are 109.5. Let's look at another common hybridized orbital in organic chemistry called the sp2 hybridized orbital. Notice here S1p2, those exponents add to 3, so that means we have 3 domains. And sp2 has 3 domains, and a domain is either a bond or an electron pair. In this carbon, I see 1, 2, 3 domains. Now remember, a domain is a bond or an electron pair. The bond can be single, double, or triple. It does not matter. It still counts as one domain. So when I look at ethylene, this carbon has 1, 2, 3 domains. Now that tells me the superscripts add to 3, an sp2 hybridization. And this is the key. sp2, in terms of its molecular geometry, is known as trigonal planar. It lies flat on a piece of paper. All lies in the same plane. This is so critical for organic mechanism that the carbon itself and the hydrogens leading out to the next carbon and its hydrogens are all in the same plane. Trigonal planar. When we hybridize, we promoted one of the s electrons into the p orbital, and that gave us an sp2 hybridization. And the last hybridization, very common in organic, is called an sp hybridized orbital. Notice the s and the p add to a total of 2 for their superscripts. That tells me there's 2 domains. Notice this carbon in acetylene, it has 1, 2 domains. When I say the word domain, it could be a single bond, a double bond, or a triple bond, or a lone pair. All of those count as a single domain. So even though acetylene has a triple bond, it still counts as one domain. Here is a single bond, still counts as one domain. So a total of 2 domains simply means that we have an S1, P1, 1 plus 1 gives us 2 for 2 domains. This means that the molecular geometry for this molecule is linear, with a bond angle of exactly 180 degrees, just like a straight line. This also is a 180 degree bond angle. So it's a very linear, oops, I put the 0.8, 180 degree bond angle. So an sp3 is 4 domains. It will always be tetrahedral. That means the bond angle is about 109.5. Think about its geometry, and you have these like the base of a pyramid with a straight up point. An sp2 hybridized tells me that there's 3 domains. Its molecular geometry will be trigonal planar, just like an equilateral triangle. So just draw an equilateral triangle with the bond in the center, and you've got that molecular geometry. And these will all be 120 degrees. So a flat triangle. And of course, sp tells me there's 2 domains. And 2 domains means that it's a linear molecule with a bond angle of 180 degrees. Shall we try some? What is the hybridization at each of these carbons? And let's just look at this structure first. Let's number 1, 2, 3, 4, 5, 6, 7. We have 7 carbons in that particular structure. Carbon number 1 has 1, 2 domains. And therefore, we know that any compound here would be an sp hybridized orbital. 2 domains. Carbon 2 also has 2 domains. So it is also an sp hybridized orbital. Carbon 3. Here's carbon 3. Notice that it has 4 bonds. So that means there's 4 domains. That means that it's an sp3 hybridized carbon. Here's carbon 4. Carbon 4 has 1, 2, 3 domains. Remember that even if it's a double bond, it still counts as 1 domain. So that's an sp2 trigonal planar 120-degree bond angle. Carbon 5. Carbon 5 has 1, 2, 3 domains. Therefore, we know it's an sp2 hybridized carbon. Remember, even though it's a double bond, it's still 1 domain. Carbon 6. Carbon 6 has 4 single bonds, so that's 4 domains. That tells me that it's an sp3 hybridized carbon. And the last has 4 single bonds, telling me that 4 single bonds is 4 domains, so that's an sp3 hybridized carbon. Let's try this carbon here. I count 1, 2, 3 domains. That's sp2. This carbon is also sp2 with 3 domains. This carbon has 3 domains. It is also sp2. And finally, something different here. That particular carbon has 4 domains. So it's sp3 hybridized. It's become easier if you just practice. Here's a carbon with 2 domains. So therefore, it's linear with an sp hybridization. And this carbon has 3 domains. Therefore, it's an sp2 trigonal planar hybridized carbon. Let's talk briefly about bond strength and bond length in this particular slide. I remember learning in general chemistry that a single bond is the longest bond, and as I begin increasing electron density between the 2 carbons, like in a double bond, I decrease bond length all the way to a triple bond, which is very electron rich between the 2 carbons, and you have the shortest bond. The longest bond is the single bond. The shortest bond is the triple bond, and the in-between length, of course, would be the double. Notice that the amount of energy needed to break those bonds significantly increases with the more shared pairs between them. To break this triple bond requires 820 kilojoules for every mole of energy. To break this double bond between the carbons requires 632 kilojoules per mole. And the least or easiest to break, the least amount of energy, 368 kJs per mole for a carbon-to-carbon single bond. So the bond length decreases with increasing number of bonds. And to practice that, simply rank the indicated bonds in terms of increasing length. Here we have a triple bond. Here we have a double bond. And in this structure, I have a single bond. The single bond would be the longest, and the shortest would be the triple. And in between would be the double bond. And that's easy enough to review. I'm going to stop the video here. In our last lesson, we'll talk about the Vesper theory and intermolecular forces, two major topics left to go in our chapter.